Hello, welcome back to Module 6 on Blockchain System Architecture and Consensus Protocols. In this lecture, we will look to consensus protocols. The main learning outcomes of this module is to know how to construct architecture of blockchain-based applications, apply design patterns, compare different consensus protocols. Particularly in this lecture, we will compare different consensus protocols. A short reminder from the previous lectures. Blockchains are decentralized networks that are supported by numerous autonomous nodes. By creating a single version of reliability, blockchains allow the exchange of digital currency. Blockchains are peer-to-peer networks where value can be exchanged without the need for reliable third parties. One of the most important components in the blockchain platform is the way how consensus about the new transaction is achieved. In this lecture, we will look into the evaluation criteria of consensus protocols. Then we will have the survey of consensus protocols, and then we will evaluate different consensus protocols. Let's start with evaluation criteria for consensus protocols. The blockchain protocol layer includes consensus algorithms. Consensus is a way of coming to an agreement. It evaluates the network's ability for independent nodes to reach consensus on a single version of the truth. It does not even matter whether participants of the system trust each other particularly or do not trust at all. All the way, they need to agree on a certain principles of functioning that would be common for all of them. In this way, the consensus becomes essential to enabling transactions in blockchain systems. Consensus is the process by which a group of peers or nodes on a network determine which blockchain transactions are valid and which are not. There are many different types of consensus mechanisms depending on the blockchain and its application. While they differ in the energy usage, security, and scalability, they all share one purpose. Here we will look to a few characteristics like scalability, centralization, security, and cost. Scalability is measured in transactions per second. How fast can a consensus algorithm process and verify growing amount of data? Bitcoin processes 4,6 transactions per second. In comparison, Visa does around 1,700 transactions per second on average. So the limitation of blockchain models is that achieving scalability usually requires sacrificing decentralization, security, or at some degree both. For instance, a scalable and decentralized network will need to incentivize a large number of active participants to achieve high security. A scalability and secure network will generally raise the cost of running a node at the expense of decentralization. Furthermore, decentralized and secure networks keep node requirements low and the cost of attacks high, but end up with scalability bottlenecks. Decentralization. Blockchain is a decentralized peer-to-peer network. Blockchain is a transparent and immutable network that enables append-only records. Therefore, it's easier and more secure to share information among different parties. In blockchain, firstly, power decentralization takes place politically as no central entity controls the system. Secondly, blockchain decentralization happens on the architecture level. the infrastructure has no single point of failure. Each node has exactly the same copy of the information as another node. Even if one system is tampered with, there will be other nodes to regulate the flow of information. Moreover, a single node with a change can easily be pointed out. Security. So, the blockchain contains the capability to guarantee the integrity of the shared history of validated data. Since security is understood as the amount of resources required to corrupt network consensus, it can be estimated by comparing the cost of tampering with a specific consensus method to the anticipated economic advantage from an attack. It is the consensus mechanism that ultimately determines the level of security, speed of transactions, and scalability of a network. Cost. Cost is more than a measure. Cost here is calculated based on the energy consumption of the necessary computational resources. To encourage nodes to act honorably, the cost of maintaining a node in the network must be lower than or equal to benefit of doing so. Now let's go into the different consensus protocols. Currently, there exists a wide range of consensus methods. We will discuss few, the most commonly used. These include proof of work, proof of stake, delegated proof of stake, proof of authority, and practical Byzantine fault tolerance. Proof of work became popular for being the consensus mechanism behind Bitcoin. It enables the selection of miner that must also be a node. Miners compete in order to solve complex mathematical problems. The miners that solve the puzzle first will be eligible to mine the next block of the chain. Miners contribute significant processing power in order to hash and propagate block data and become eligible to mine blocks. Therefore, this process is costly for the miner and wasteful to the environment due to their competition and the complex computations needed to win the mining race. Proof of work proved to be useful and proved to be secure for Bitcoin. However, it requires large amounts of computational resources and energy to generate new blocks. The operating costs behind proof of work are notoriously high. This acts as a barrier for entry for new miners, leading to concerns about centralization and scalability limitations. When a hash function is applied to the message that is signed with the digital signature, the final 256-bit hash is produced. Now, to further influence this final hash, a number called nonce is added to the end of the transaction. The role of this number is to influence the final hash so that it will begin with a certain number of consecutive zeros. As inverse computation is not possible in this form of cryptographic hash function, the only way to obtain this nonce is through trials and errors. Figuring out the nonce, which would require extensive time and computational work, would prove that someone has done the work required to identify this number. Hence, this process is called proof of work. Once the nonce has been identified, other participants can run SHA-256 on this number to instantly confirm the validity of the nonce. All this information is then compressed into a block and added to a chain. When a new block is formed, it also contains the hash of the previous block, which is also one of the factors that dictates the hash of the new block. Proof of work operates on a principle that it is expensive to add a new block of new transactions to the blockchain. The cost of a block is the work that has to be done, calculation, or better known as mining. A node has to calculate the correct hash for the block in order to secure the block and place it on the blockchain, in turn freeing another new block. A correct hash is a hash that fits the predetermined difficulty pattern. In Bitcoin's case, this is a number of leading zeros. Hashing, or mining. The hash has to be calculated using 3 known values inside the block: the previous block's hash, the hashes of the transactions contained in the block, the Merkle root, and the block's creation time. As all these 3 values are fixed, hashing them will always produce the same, most likely incorrect result. To be able to alter the hash outcome, a 4th string is added, so-called nonce. By continuously randomizing these nonce, the node can find the correct hash that fits the difficulty pattern. Once the right nonce is found, it is placed inside the block, and the calculated hash is added to the block's header, securing it and its contents. The signature acts as a sort of lock, locking the block, preventing further changes of the transaction stored inside. Reaching consensus. If the node is the first one to find this nonce, it broadcasts the complete block to all other nodes, who can then verify the work that was done. The nonce that can thus be considered as the proof of work. By hashing the previous hash, transactions hash, creation time, and the found nonce together. This then produces the same correct hash signature. If it does, the node considers the block valid and adds it to its copy of the blockchain, discarding its own or any other version of the block. If more than 50% of the nodes do this, a state of consensus is reached, and the block is definitely valid. In the course of time, the entire network will have added this block to its blockchain. The node that found the nonce will then receive an award, for example, Bitcoin. This reward provides incentives. To compensate for increasing hardware speed and varying interest in running nodes over the time, the difficulty is determined by moving average targeting and average number of the blocks per hour. In Bitcoin's case, this makes sure a new block becomes available roughly every 10 minutes. If blocks are generated too fast, the difficulty increases. If they are generated too slow, the difficulty decreases. Example of proof of work is in the Bitcoin blockchain. Its algorithm has influenced the consensus algorithms of numerous other blockchain projects too. However, it is slow as discussed above. For instance, Bitcoin scalability is restricted to validating 1 megabyte of transactions data every 10 minutes. The proof of work algorithm has also influenced development of the technology. For instance, the application-specific integrated circles, miner, are pieces of the specialized hardware that are used to compete in the Bitcoin's proof of work competition. In practice, specialized mining equipment and high energy cost have resulted in the Bitcoin network's mining becoming de facto centralized. Proof of stake relies on the number of tokens held by nodes in order to determine who will validate the new block. Nodes must stake a specific amount of tokens. The more tokens a node stakes, the more the changes of the node being the validator for the next block. This process saves computational energy and does not require special mining equipment. Therefore, it is much more environmentally friendly than proof of the work. Moreover, it has a fast execution time and the transaction fees are relatively low. However, proof of stake favors nodes holding large amounts of tokens, while some blockchains also require locking tokens for an extensive time period. Delegated proof of stake is an evolution of the proof of stake, as it allows users to vote for the next block validator by spending a number of tokens. Therefore, this is a situation of token holders electing delegates rather than creating blocks themselves. Delegated proof of stake is sustainable, scalable, and efficient in terms of energy consumption. It eliminates the need for computational power by token owners. The inclusion of the voting mechanism ensures a degree of security among peers. It is relatively more centralized than proof of stake. This is because the delegates have the authority to define protocol rules and the status of transactions. Token holders vote on delegates by committing their tokens into a centralized staking pool, which corresponds to a specific delegate. Example of the application of the delegated proof of stake is EOS blockchain-based platform. It enables the development of business applications or dApps. EOS supports secure access and authentication, permissioning, data hosting, usage management, and communication between the dApps and the Internet. In principle, it is quite simple and similar to the Ethereum platform, but it uses the delegated proof of stake for reaching the consensus for transactions. To compare the proof of stake and the proof of work, the following can be observed. Proof of stake is more energy efficient and thus less costly than proof of work. Proof of stake consumes less energy. To the degree of decentralization in proof of stake is determined by the algorithm that structures the lottery. High wealth concentration can jeopardize the integrity of the proof of stake networks. Proof of stake is less secure than proof of work in determining which chain is valid. Proof of authority. This mechanism involves a high degree of centralization. Proof of authority is a modified form of proof of stake, where instead of stake with the monetary value, a validator's identity performs the role of stake. In this context, identity means the correspondence between a validator's personal identification on the platform with the officially issued documentation for the same person, meaning certainty that a validator is exactly who that person represents to. Proof of authority is ideal among governmental or private institutions and entities, where a centralized party assigns nodes with the responsibility of creating new blocks. Therefore, proof of authority cannot be trusted for public blockchains, but is rather suitable for permissioned networks. However, even in centralized ecosystems like a governmental authority, the authority or the administrator may be malicious. This aspect carries the risk of modifying transactions and the history on the chain. In ideal instances, proof of authority is very secure as the validators are known and usually trusted by participants. The network is fast and efficient in terms of energy consumption. The concept behind proof of authority is that conventional internal procedures can be executed with high efficiency, speed, and low transaction costs via the use of blockchain technology. The main disadvantage of such network is the lack of decentralization. The Byzantine generals problem describes a scenario where a system may fail if its components cannot agree on a concrete strategy. The problem assumes that some fractions of the system is corrupt and will act against the system. The Byzantine fault-tolerant system should be capable of achieving finality regardless. Let's assume that the different Byzantine generals command their respective unit at different positions outside the city they are about to attack. The generals can communicate with each other through messengers, sending one messenger at a time. The Byzantine generals must have coordination and agreement on a particular plan of action for successfully attacking or retreating. If all the generals attack at the same time, or all of them retreat at the same time, there is no problem. However, if one general retreats while other attack, or attacks while other retreats, the general would end up losing. Therefore, the outcome will be bad for all of the generals and their units. Another important point in the Byzantine generals problem is the fact that some of the generals are not loyal. These generals could try sending the wrong or manipulated information to the other generals for confusing them. The Byzantine fault-tolerance model could help in resolving this problem. The generals would need an algorithm that could guarantee the following conditions. All the loyal generals would act and agree on the same plan of action. The loyal generals of the Byzantine army would not follow a bad plan under the influence of traitor generals. The loyal generals would follow all the rules specified in the algorithm. All the loyal generals of the Byzantine army must reach a consensus irrespectively of the actions of the traitors. Most important of all, the loyal generals should also reach an agreement on a specific and reasonable plan. How does BFT apply to blockchain? On blockchain network, each node is considered a Byzantine general that contributes to a network's consensus. The foundation of Byzantine fault tolerance is visible in a scenario where all nodes repeat an incoming message. If a node repeats the incoming message, then it clearly indicates that it does not have any issue of faults. Byzantine node refers to the traitor node, which could lie or mislead other nodes in the network intentionally. The Byzantine node could also mislead or lie on the node that are involved in the consensus protocol. Byzantine fault tolerance, or BFT, helps in overcoming the challenge by reducing the impact of malicious nodes. It lets the honest nodes and malicious nodes do their own work without affecting network properties and performance. The practical Byzantine fault tolerance mechanism ensures a practical Byzantine state machine replication for tolerating Byzantine nodes or failures. The most prominent assumption regarding practical BFT refers to the fact that the total number of nodes in the network must be greater than 3Fs, where F is the number of dishonest or faulty nodes. The practical BFT node deviates slightly from the pure Byzantine generals problem by adopting a command or lieutenant approach. all the generals are not equal in the private BFT. Then the model works as follows. First, clients send requests to the leader node for invoking a specific service operation. 2. The leader node could then multicast the request to backup nodes in the network. 3. Nodes could ensure execution of assigned request followed by sending a relevant reply to the client. And 4. The client would then wait for F+1 replies from various nodes with a similar result. In this case, F denotes the maximum number of nodes with possibility of faults. The outcome is basically reflective of the result from the operation. It is important to ensure that nodes are fulfilling the important requirements for Byzantine fault tolerance in blockchain. The nodes must be deterministic and begin with the same state of practical BFT. The final outcome would imply that all honest nodes would reach an agreement regarding the order of the record. The nodes could either accept or reject the record in the final result. Interestingly, practical BFT utilizes a round-robin type format for modifying the leader node in each view. Advantages of the practical BFT. First, flexibility and speed of transactions. It can provide the assurance of transaction finality without any requirement of confirmations such as proof of concept. Then the nodes in a practical BFT model agree on the consent block. The block is considered as final. Second, low energy consumption. Practical BFT does not involve intensive computational efforts, thereby leading to a profound reduction in consumption of electric energy. However, practical BFT also has a certain amount of setbacks. For example, the practical BFT model is applicable only in its classical form. Therefore, it is restricted to small consensus group size to avoid the cumbersome volumes of communication needed between nodes. Other consensus protocols. Proof of elapsed time, POET, aims to achieve fairness among participants via lottery system to determine block winners. The lottery mechanism is transparent and assures a transparent ecosystem. Leading microchip manufacturers Intel developed the proof of elapsed time consensus algorithm in order to equally share the changes of block creation among the network. Nodes enter into a sleep mode and perform various tasks to exchange network efficiently. Each node sleeps according to a different wait time. The node that wakes up first is the winner in the next block. Then the mining process is similar to proof of work, but without a hassle of high computational power. POET is mostly ideal for private blockchain networks such as Hyperledger Sawtooth. Proof of history. As the name suggests, proof of history provides proof of historical events. It is developed by Solana. Proof of history allows for timestamp to be built into the blockchain itself, verifying the passage of time between transactions without having to rely on other nodes. This timestamping method is enabled by that's known as SHA-256, sequential hashing verifiable delay function. It works by taking the output of the transaction and using it as input for the next hash, which enables everyone to clearly see which event took place in a particular sequence. As the VDFs can only be solved by using single CPU, proof of history severely reduces the processing weight of the blockchain, making it faster and more energy efficient than many of its counterparties. Proof of importance, POI. Proof of importance selects its miners based on the certain criteria in the process called harvesting. Common factors include the number of the size of transactions in the last 30 days, amount of vested currency, and network activity. It is based on these factors that an importance score is attributed to nodes. The higher the score, the higher the probability of being chosen to harvest a block and receive the accompanying transaction fee. Though similar to the proof of stake, proof of importance uses an additional matrix that does not away with the former's tendency to inherently reward the rich by taking into account participants' overall support of the network. As such, simply staking high of proof of importance does not necessarily guarantee a change of winning the block. Proof of activity. Proof of activity is a hybrid of the proof of work and proof of stake consensus mechanism. It is used by Decred and Esper blockchain projects. In proof of activity systems, the mining process begins like proof of work, with miners competing to solve the elaborate mathematical problem using immense computing power. Once a block is mined, however, the system switches to resemble proof of stake, with the successfully generated block headers being broadcast to the proof of activity network. A group of validators are then randomly selected to sign off the hash validated the new block. Like the proof of stake, the more crypto the validator holds, the higher the chances of being selected. Once every chosen validator has signed the block, it is added to the block network and ready to record transactions. The block reward are then shared among the miner and validators. Though the proof of activity system was designed with the intention of combining the very best features of proof of work and proof of stake while avoiding their shortcoming, it has criticisms for its energy-intensive mining phase and inherent partially towards validators holding the greater number of coins. Proof of burn. Another more sustainable alternative to Bitcoin's proof of work algorithm is proof of burn. Proof of burn, miners gain the power to mine a block by burning or destroying a predefined amount of tokens in a verifiable manner, namely sending them to an Ether address where they cannot be recovered or spent. The more coins burned, the greater the chances of being randomly selected. Unlike in proof of stake, where miners are able to retrieve or sell their locked coins should they ever leave the network, burned coins are irretrievably lost. This method of requiring miners to sacrifice short-term wealth in order to gain the lifetime privilege to create new blocks helps to encounter and encourage long-term commitment from miners. The act of burning coins also leads to the coin scarcity, limiting inflation and driving up demand. Proof of capacity or proof of space. Unlike the majority of its predecessors, which grant mining rights based on the computational power of coins staked, proof of capacity, also known as proof of space, bases its mining algorithm on the amount of space available in the miner's hard drive. In proof of capacity, miners generate a list of all the possible hashes beforehand in a process called plotting. These plots are then stored on the hard drive. The more storage capacity a driver has, the more possible solutions. The more solutions, the higher the chance of processing the correct combination of hashes and winning the reward. As it doesn't require extensive or specialized equipment, proof of capacity opens up opportunities for the average person to participate in the network. As such, it is a less energy intensive and more decentralized alternative to some of the more prevalent consensus mechanisms covered in this guide. So after this overview of the different consensus protocols, after the specific look into some specific consensus protocols, let's see some evaluation of these protocols. Based on the existing research on the blockchain consensus algorithm, the design of the blockchain consensus algorithm is evaluated from three perspectives: efficiency, security, and fairness. The efficiency dimension includes efficiency, scalability, and energy consumption. Efficiency is mainly reflected in the delay of the definitive or probabilistic final consensus after the block has been changed. The scalability is reflected in the speed of the blockchain being chained and the number of transactions contained in each block. The ability of the process given number of transactions per second. Energy consumption refers to the power consumption and the communication overhead in the process of reaching consensus. The security dimension mainly includes forking, the cyber attack, privacy protection, and BFT. Forks in Bitcoin lead to waste of the significant amount of computational power. Resistance to the cyber attack is one of the uncompromising metrics of all consensus algorithms. For privacy protection, systems pursue identity, hiding, and transaction exposure. The BFT means that the blockchain system can tolerate Byzantine fault nodes. The fairness dimension mainly includes the degree of decentralization, free access of nodes of the blockchain network, and whether the accounting opportunities are equal. The degree of decentralization refers to the system operation phase rather than the design phase. The consensus algorithm that supports the free entry and exit of nodes is more consistent with the actual need of the consortium blockchain and the public blockchain. More competition for the bookkeeping rights is a manifestation of whether the blockchain system is democratic and fair. The existing blockchain consensus algorithm is scientifically balanced in three dimensions of effectiveness, security, and fairness to suit various scenarios. The 10 metrics of the three dimensions cannot be satisfied at the same time. Hence, in various scenarios, different weight of metrics is chosen, and the algorithms that satisfy more high weight factors are adopted. Based on the intrinsic relationship model of the above-mentioned metrics, guidelines need to be provided for designing the customized consensus algorithm for different demands and the various scenarios. This summarizes the overall lecture on the consensus mechanism, on the consensus protocols. If you are interested in learning more about them, I recommend to look into these references. Thank you for your attention.